My name is Gerd Bruder. I'm an associate professor for virtual and augmented reality at the University of Central Florida. And it's a pleasure being here today and having the opportunity to share some of my research. Now, in this presentation, we will look at embodied agents in augmented reality. So please follow me. Now that's better. You are currently seeing me as captured by a camera, which is similar to a video see-through AR setup, which allows me to show you some of my research in this field. Now, with current AR head-mounted displays like this Microsoft HoloLens 2, we can anticipate how we will interact with our surroundings in the future when everyone has AR naturally integrated in their eyeglasses or their contact lenses. Right? With AR displays like this, we don't necessarily need smart speakers in your home. Like, for instance, the smart speakers you have to interact with Amazon's Alexa that you might have in your living space and in other rooms in your house, right? Nowadays, those AR glasses that I'm wearing right now can take over that functionality, right? So for instance, I can say, hey, Alexa.
Hi, Gerd.
But we can also add visuals on our AR display, effectively giving Alexa a body you can see standing in your physical space. Oh, there you are. Right. Now, Alexa, could you do me a favor and turn on the light in the room?
Okay. Done.
Thank you. Now, Alexa, could you please give me some privacy? I don't really want you to hear what I'm going to tell those folks out there about you, okay?
Sure, just call me if you need me.
Now, what you've just seen is real. It is a version of a prototype of an embodied agent we developed here at the Synthetic Reality Lab at the University of Central Florida. Of course, behind the scenes, nothing's perfect, but we nowadays have all the components we need to make this a reality, even in someone's home or scaling up in a smart city context. What we need is an AR display on your head, which does slam tracking and essentially knows where it is relative to the environment, plus smart connected IoT devices in the environment that uses self-localizing and self-organizing architecture, like connecting a physical affordance like the light switch in the real world to the digital affordance that allows us to trigger the IoT light bulb so that essentially the light bulb can turn on or turn off. And the effect is that, well, a computer graphics character can interact in the space in AR, walking around, walking towards physical affordances, interacting with them, and seemingly like any other real person, flip a light switch, or rather pretend to do so, and turn lights on and off in the space, right? This way, AR allows us to connect the physical world with the digital world, in particular physical affordances with digital affordances. Now we evaluated our prototype and compared the embodied Alexa with an Alexa voice agent, like the one you may have at home. So we are curious to see if participants may feel more confidence and trust in Alexa actually doing what the user is asking her to do, if she does indeed have a visual body. Now, details are in the reference shown at the bottom of the slide, but let me give you the cliff notes. Now, first of all, let's start with what we call awareness tasks. Here, we asked Alexa if she could check the status of something for us in the real world. For instance, if I asked her if there's anyone at the front door. In the voice agent condition, all we should do is say no. Right? While in the embodied condition, we would actually see her walk there, come back, and then say no. Now, our results show that having a body perform this task greatly increased participants' confidence and trust. Now, second, we assessed what we call influence tasks. Here, we asked Alexa to influence the real world like for instance, turn on a light in this room or in a different room, we can't see. Now in the embodied condition, she would walk there and come back, for instance, walk out of the door and then come back through that door. While in the voice condition, all we would hear is her voice telling us that she has done the task. Right? So again, the ability to see her visual body greatly increased participants' confidence and trust in her actually completing this task. Now, last but not least, if we asked her to give us some privacy, you can see the results. What we found is pretty in line with what you might think of your Alexa at home. So no one really trusts a voice agent with privacy. However, once we gave her a body, you can see that her body leaving the room actually makes a big difference. It makes us believe it more that she's actually giving us some privacy, not fully, but significantly more than with her just having her voice telling us that she's now giving us some privacy. Now, if I had to condense those results into some general take-home messages, I would probably say that giving her a visual body has a lot of benefits with respect to increasing one's trust in Alexa. The first one is seeing is believing. Clearly, we are inclined to believe what we are seeing much more than if we are just hearing it, right? Further, seeing actions speak louder than words, right? For instance, if we see her leave the room, at least we see that she understood that she has a task to do, right? And third, when it comes to trust and privacy, then out of sight is out of mind. An embodied Alexa can leave the room, something a physical home speaker device that you may have at home, it just can't do that, right? Additionally, to those results, we also found that such an embodied agent in a role as a home assistant feels significantly more like a social entity than a traditional voice assistant in your home. Right? With our social presence questionnaire, we found that giving her a body makes her significantly more spatially present, socially richer, and overall, well, more engaging. So if you want more from your agent than just being someone who accepts your commands and performs them, more something like a social entity, then giving her a visual body is probably the right way to go. Now, in the last examples, Alexa could walk around and interact with IoT devices, for instance, by pretending to flip a light switch, but she could not actually influence the light switch in the real world. She couldn't actually flip it. Now, what if she could? What if an AR agent could, in fact, exert influence over objects like that in the real world? Now, to explore this idea, we built a prototype in our lab, which you can see here. So a table where you could be, as a participant, sitting on one side, and then the agent would be sitting on the other side, and together you could play a game. And here's how it works. So we started with a motorized translation stage, like a common 2D plotter. Then on top of that translation stage, we mounted a strong electric magnet. The effect is that the plotter can now move the magnet around in 2 dimensions, as you can see here. Now, on top of that, we then added table surface, on which we then placed a magnetic game piece, which then could be moved over the table and essentially dragged by the magnet underneath the table as if this game piece was actually moving by itself. I hope you can see that in the center video. Now, last but not least, we then registered this game piece with our AR agent's hand to effectively give the illusion that it is in fact the agent that is moving the game piece over the table. Now let's have a closer look at how this looked like from our participants' perspective. Now here you can see our participant sitting on one side of the table and Alexa on the other side. And our study would start with some general verbal voice interaction, right? So saying hi, etc. And then she would start the game by rolling the dice. So here we simulated that with a random number generator. So you can see she is moving her game token 1 field forward. Then it's participant's turn. Let's see. So they they rolled a 3, so they are now moving their game tokens 3 fields forward. Then it's Alexa's turn again. Let's see what she rolls. I think you get the idea. Now, we ran a full study, letting participants play with Alexa with either virtual game tokens or those physical game tokens that you've just seen, where Alexa could either influence a virtual token or those physical tokens. And you can see that our results clearly show that participants felt much more co-presence if Alexa could influence the real world, if she could move those physical game tokens over the table, than just being able to move and influence virtual game elements on that table. Participants also felt that the gaming experience was much more enjoyable when she could influence the physical game table and it wasn't essentially limited to virtual objects. And last but not least, we also found that our participants showed much more natural behavior when in the condition when she could influence the real world. For instance, they looked more at the agent, less on those game tokens, and they, in a way, treated her more like a real person. Now, one more interesting aspect we observed is the latency between the agent's virtual hand movements and the onset of the physical tokens movement. And essentially what you've seen in the video before is that you could probably see that there was a slight delay between the physical game tokens movement and her hand movement. And we found that it matters a lot. Right? So what we did was we repeated the study and we honed in on this aspect of latency. Now, the interesting aspect of latency is that it can actually be positive or negative. In this case, we can have positive and negative latency, meaning that the token can move right after the virtual hand is moving, right before the virtual hand is moving, or right when the virtual hand is moving. Right? Now, we expected that the optimal case would pretty much be when they're all in sync. Right? So when the virtual hand and the game token are moving exactly at the same time with what you would call zero latency. But this is not actually what we found. Instead, we found that our participants considered a slight delay of about 100 milliseconds more natural than a perfect synchronization, which in a way makes sense, right? Seeing the cause of the effect first, the virtual hand, and then the effect, the token starting to move, might just feel a little bit more like the real world, like what we are used to, than seeing both of them exactly synchronized. Now, overall, giving AI agents such control of the real world has a ton of potential. And we're getting closer to actually seeing products that can do those things in an arguably nicer form factor than those contraptions we built in our lab. For instance, you can now buy actuated game boards where the tokens can move by themselves, right? So you can see it hopefully in that video. Now, of course, what those game boards don't have right now is an AI agent that's sitting opposite from you and moving those game tokens, right? But give it a couple of years and we could actually register those game boards with those agents and then maybe give players the opportunity to have an agent opposite from them at their choice, right? Either with no agents or with a visual agent sitting on the other side of the table. So thinking ahead to the next pandemic, when you're cooped up at home or your children have no one to play with, wouldn't it be nice if they had an AI agent to play with using a game board like that? I would certainly think so, at least for myself. Now, I also want to give a quick shout out to Susanne Schmidt and Frank Steinicke and the team at the University of Hamburg, who actually developed a larger example of such physical influence. Here the AI agent, this character you can see there, is interacting with a real world golf ball that is actuated and moves in line with the AR agent. So in a certain range, you can actually scale up those ideas. Now, the potential of such AI agents sounds great, but in practice, we are still facing a lot of challenges. Probably the biggest one is resolution. None of the AR displays we have today can match the acuity of our human eyes. For instance, a study by Paul Ekman back in the 1960s showed that we as humans are capable of resolving another human's facial expression for distances of up to 40 meters. But when we repeated the same task in VR with an HTC Vive head-mounted display, we found that this distance was reduced to just 3 meters. After 3 meters, you can still see that there is a face, but the resolution is not sufficient to distinguish most facial expressions. Not just micro expressions, but also macro expressions. Of course, it is getting better, but only very slowly. The most recent generation of displays now has twice that resolution of the HTC Vive, meaning that you can now see faces for distance of up to 6 meters. Well, it's still a far cry away from the real world with 40 meters. You would pretty much have to increase the resolution tenfold to reach that, which won't happen in the next couple of years. So, since the display hardware is still lacking, we were wondering, well, maybe there is something we could do in software. Keep in mind, in VR and AR, we don't necessarily have to replicate reality, right? So let's try something. Now, can you see it? Okay. And now we are back to normal. Now you can see my facial expression again. Now you can't. Now you can. Okay. Now, agreed, it's not 100% real, but it's not really that bad. My head is currently twice as big as before. This is what we call the big head technique. We didn't invent it. It's been pretty much around since the early computer games, where the developers were facing a similar challenge, namely that we had very low resolution screens back in the day. While such a representation is clearly not realistic, it is a bit surprising that we as humans are rather tolerant when it comes to seeing such disproportionately scaled body parts. That includes my head, my hands, my feet, and, well, other body parts, right? Just keep in mind that they don't actually grow any bigger if you use this technique. So up to recently, you could actually see this technique, the big head technique used by Meta in their metaverse. But nowadays, if you want to try the technique at home, we actually implemented a version of it using Snapchat's reality lenses. Just scan the QR code and you can use it to spice up your next Zoom call or give yourself a little bit more confidence with a bigger head when you're talking to your boss in the next Zoom call. Now, sadly, not all issues with AI agents can be resolved like that. Some issues are rather fundamental and deserve some more attention from the broader research community. We came across a particularly bad example when we are playing around with so-called dark mode graphics on a Microsoft HoloLens. The idea behind dark mode and light mode graphics is pretty simple. You either present dark text on a light background, called the light mode, or light text on a dark background, called the dark mode. However, when you present imagery on an optical see-through display, such as the Microsoft HoloLens, you're limited by the optical properties of that display, which can add light to your eyes, but not take light away, essentially preventing light from reaching your eyes when this light is coming from the environment. Now, what it means is if you render black on some pixels on the HoloLens, these pixels in fact become not black, but transparent, meaning you can see whatever is behind those pixels in the environment. Now, it's not a big problem for AI user interfaces in general if your only purpose is hoping to present some text that's readable on the AR device. But if you think about AR agents, and in particular that some agents, just like people, may have different skin colors, it does become a major issue. In fact, we found some troubling evidence that people with darker skin colors, such as AI agents or avatars presented on such optical see-through displays, are perceived as less opaque and in turn as less human than people with lighter skin colors. Just to to the transparency of their appearance. Now, it's pretty clear that such blind spots in our technology related to diversity, equity, and inclusion are highly troubling. We want the technology to empower users, right? Not misrepresent and disadvantage them based on their appearance. Now, while the technology is evolving to fix this problem, we are still nowhere near being able to represent the full range of human skin colors in AR or VR accurately, right? Well, some researchers suggested that people with darker skin colors should just make their skin color lighter in AR to make it more visible, right? To make it more opaque. However, I think you can see why that's not really a solution. If some people have to change their appearance just to blend in, at least that's not an equitable solution, right? But, well, here is one for you. For as long as AR skin colors don't work for everyone, I suggest we all create equity by adopting non-photorealistic colors for everyone. For everyone. Now, before I let you go, a quick shout out to my amazing collaborators on these topics, in particular Greg Welch and our team at the University of Central Florida, and of course my funding sources. So finally, a big thank you to you all for your kind attention. Thanks.